We saw that when you have two slits and coherent light shines on both slits, then the light will travel in all directions from each one, but there are certain directions where the two slits are the light's merely going parallel to a distant spot where they end up meeting. So they're not quite parallel, but pretty darn close. And that spot will be bright if this path is one wavelength different. Okay, so this mount right here is one wavelength different. Okay, that means that these are still in phase by the time they get to that spot way over there. A grating is basically saying, well, instead of having just two slits, let's have more. Lots more. And there are cool both chemical as well as mechanical processes of making like 600 lines, 600 slits every centimeter, or even more than that. You get some really tight slits. Okay, and so the question is, well, what does that do? Why is that an advantage? So let's go ahead and draw a few slits that are all the same spacing apart. So these all have the same spacing. Okay. Now, if we're looking at that bright spot way over there on a distant screen, so all these are pretty much parallel to each other, then when I look at this next ray, all right, well, it's off by one wavelength from this one and off by two wavelengths from that one. So this point right here is still in phase with that one. So that's going to contribute. That's going to add to it. So now we have, here we had 2 times the light of one. We'll now have 3 times the light of one. And we can continue that as we look at all these other light rays coming. That there's going to be a line such that the phase at each one of these is all the same. They're all in phase because the path lengths are all one wavelength different from the previous. So even on this far one, each of those is a wavelength, so that the total path between here and here is 5 wavelengths. That's still in phase with this one, as were all the other ones. And so now, with all these slits, that one spot way over here that obeyed 2-slit interference for a maximum, a bright spot, is now getting lots more light getting there. So it ends up being really bright. And so a grating has one benefit of having very bright peaks instead of the dimmer peaks from just 2 light sources. Okay, now there's a much more important difference that this does too. Let's take a look at the example if our slits are not, or our position is just slightly away from that one point of bright interference. So let me draw all these slits. Okay, and at that angle, there's a spot right exactly along that angle that is a bright spot. And we're going to just slightly turn, so we're looking at a spot just to the side of it, and see, well, how bright is right next to it. So if we decrease this angle just slightly, okay, so we decrease this angle just slightly, such that the path difference now, instead of 1 wavelength, let's say it's 0.9 wavelengths. Okay, which would mean down here, this is going to be 1.8 because it's twice that, just like this was twice that. Oops, that's supposed to be a wavelength. Okay, this would be 1.8 wavelengths. If we keep doing this, it will be 2.7 wavelengths, 3 times that one, and so on and so forth. Okay, and so the question is, well, this isn't too far off from a full wavelength. That should still add pretty good. So I don't see a problem here. This is, pretty close to a wavelength different from that. But what if we add these all up together? Let's go ahead and list the differences. This one we'll call 0. The phase here is 0, or 0 wavelength. This one is 0.9. We'll just do these all in terms of wavelength. And then we have one that is 1.8 wavelengths different. And then 2.7, 3.6, 4.5, 5.4, 6.3, 7.2, 8.1. Okay, I'll just stop there. We can continue on. Alright, so yes, it's true. 0.9 wavelengths isn't too far away from 1 wavelength different from this one, and so these should be adding constructively pretty good. but all the light rays are adding together. So what if I look at this one right here compared to that one? Well, if I look at that one compared to that one, that is 4.5 wavelengths different from that one, which is completely destructive. So I can look through all these and I can say that one could cancel with that one. Now again, I said that all of these are interacting together, but we can do this process to see what is the net effect. Well, 4.5 was exactly an odd, or a half wavelength, a multiple of a half wavelength different than that one. Well, 5.4 wavelengths is an overall odd, or sorry, a half wavelength different than 0.9. Okay, so this is also a 4.5 wavelengths different. So that's going to cancel with that one. And the same is said with each of these pairs. They all cancel. Which means I know I can continue this on quite far. But what it means is that even when I change this direction ever so slightly, I get a lot of cancellations that I didn't have with just the two slits. The two slits, that's not a very big cancellation at all. Okay, that's just a little bit dimmer. Okay? But when I have many slits, I have enough opportunities for cancellations. And so on the screen behind a two slit, sorry, my pen's not being cooperative. On a screen behind a two slit, I get these kind of broad, evenly spaced bright spots going down the wall. Those are all supposed to be evenly spaced. Okay? But for a diffraction grating, wherever these were bright, at that spot, I do get a bright spot. But as soon as I move slightly away, it gets dim really fast. And so the end result is I now get these tight peaks that go to zero very tightly. They all should be the same width. Forgive my drawing here. It should be very narrow. And so this separates out these two. These ones are smoothly continuing one to the other, but these ones get dim really fast. Okay, so the biggest thing a diffraction grating gives us is the ability to separate peaks out really clearly. I can see that this one is very different than this one. Now, if I'm shining just one light, red light, let's say, a specific wavelength through here, that's not going to mean much for me. But what's really powerful is the diffraction grating is the essential tool of spectroscopy, where if I shine two wavelengths of light through, because of this principle, the change in the wavelength means there's a different spot. That, let's say this is the spot for one color, and this is the spot for the other. With the diffraction grating, I can tell those peaks apart. If this was just two slit, I would have one peak that's like that, and they merge together significantly. It would be nearly impossible to tell that there are two peaks there. I would just say it's kind of a blurry peak. Okay? But with the grating, it separates those out, and so I can actually tell, oh, I've got two sources of light here. I can see the difference. And that allows us to tell what wavelengths of light are coming from some distant source, like a star. And what's cool about it is certain material, every element, when burned, gives off a different set of wavelengths. Very discrete. That's kind of a topic for a different day. But by doing this, we can actually tell what the composition of a star is, because we can see the signature sodium lines here, these bright spots. And then we can also see, oh, there's hydrogen in there too. And so with the diffraction grating, by separating these out, we're able to see them. Now, I need to end with a little clause here. Is a real diffraction grating, the way you make it is usually by some chemical or a very fine mechanical process, and the spacing between these are generally a lot smaller than the spacing we'd have with a typical two-slit experiment. And because of that, if you remember back to the equation for two-slit, the angle at which you start to see these peaks spreads out significantly. And so we no longer can follow the small angle approximation, and we have to go with the true full sine of theta equation. And so the equations for this to find these locations are truly the same as 2 slit, but we have to use d sine theta equals m lambda. We cannot simplify this to the tangent of theta like we did before. So usually what we do is we don't usually have a wall that's the distance L away. We actually have a curved apparatus that's a set distance at all angles, so we don't have any weird geometry effect. And so with that, the angle can be measured fairly easily. So we have an eyepiece or something that moves, and we can measure that angle fairly easily. And we have to use the full sine function. So that's the important mathematical thing, is otherwise it's the same as 2 slit, but we cannot simplify this out.